In the world of tiny creatures, there's one insect so small it could sit right on your fingertip, yet so strong it has left modern science in awe. You've probably seen them everywhere, in your garden, across your dinner table, or just marching along cracks in the pavement. They travel in lines, work tirelessly, and most astonishingly, they can lift objects up to 50 times their own body weight. Sounds like science fiction? Well, it's not. It's pure biology. So how can a creature so tiny possess such extraordinary strength? Let's dive into a fascinating scientific journey where physics, biology, and engineering intertwine to uncover the secret behind this superpower that seems straight out of the superhero universe. Imagine watching an ant carry a piece of food many times larger than itself. It walks slowly but steadily, gripping its prey tightly with its jaws, its body straining with each step like a miniature Olympic weightlifter. To ants, this is business as usual. A study by Ohio State University revealed that some ant species can lift objects up to 5,000 times the weight of their neck without any damage. To put that into perspective, if you had the same strength, you could lift a double-decker bus over your head and smile while doing it. This isn't fantasy, it's fact. But to understand why, we need to begin with something deceptively simple: body size ratio. In biology and physics, there's a foundational principle called the scaling law. It states that muscle strength scales with cross-sectional area, which is the square of length, while body mass scales with volume, or the cube of length. Sounds technical? Let's simplify. If you double the size of an ant, the area of its muscles increases by 4 times, but its mass increases by 8 times. That means it gets heavier way faster than it gets stronger. This explains why small creatures like ants have relatively greater strength than larger animals. If a human had the proportional strength of an ant, they could carry a battle tank on their back. This isn't magic, it's physics. In the world of strength, being small is actually a pretty big advantage. One of the key components of the ant's strength lies in its neck. Contrary to what we might assume, an ant's neck is far from fragile. It's a biomechanical marvel, designed with a perfect balance of flexible tissue and a tough outer skeleton. In an elaborate experiment, researchers at Arizona State University used a high-powered centrifuge to apply increasing force to the ant's neck until it failed. The result? The ant's neck could withstand forces 3,400 to 5,000 times its body weight before giving way. But how can such a tiny joint endure so much pressure? The answer lies in the unique transition zone between the exoskeleton, or outer shell, and soft tissues. Instead of an abrupt end, this area features a gradual layered shift between hard and soft material, which evenly distributes stress and prevents snapping. In short, the ant's neck is a masterpiece of biological engineering, tiny but incredibly powerful. If the neck is the joint, the engine behind the lifting lies in the ant's muscles. Even though they're small, their muscles are densely packed with fibers, and honestly, they function with exceptional efficiency. An average ant has more than 900 muscle bundles working in sync to lift, stabilize, and move. Particularly the mandible muscles, those that power their jaws, are considered among the strongest muscles relative to size in the entire insect world. When lifting an object, ants don't just use their jaws. They actually engage muscle groups across the thorax and abdomen to balance and maneuver, kind of like a human weightlifter coordinating their entire body for a lift. This fluid cooperation allows ants to carry and transport oversized loads without losing balance. Unlike humans, ants don't have bones inside their bodies. Instead, they are protected and supported by a lightweight but durable exoskeleton, a kind of natural armor. This exoskeleton doesn't just provide protection, it acts like a mechanical support frame, relieving their muscles from the burden of supporting their own body weight, allowing them to focus entirely on lifting and carrying external loads. This biological design makes ants ideal weightlifters in the animal kingdom, maximizing efficiency without the need for bulky internal bone structures. Ants aren't just strong as individuals, they're masters of teamwork. When faced with a load too heavy for one, ants coordinate seamlessly to divide the weight and apply force from multiple angles. Have you ever seen a group of ants carrying a large insect? From afar, it might look like the object is moving on its own. But up close, you'll see a well-organized team of ants, pushing, pulling, balancing, and steering together with astonishing precision. This is more than just brute strength, it's strategy. The ant's incredible strength has inspired scientists and engineers worldwide. Researchers are studying their neck structure, muscle layout, and biomechanics to design miniature robots capable of performing tasks in extreme environments, like deep space or inside the human body. So, some experimental ant-inspired robots are already being tested to move objects in tight, delicate spaces, places where, honestly, humans just can't reach. Other teams are working hard to replicate the hard-soft neck transition in artificial joints, aiming to create durable, flexible robot limbs that don't rely on super complex mechanics. It's clear, ants may be small, but they're teaching us some really big lessons in technology and design. Now just imagine this, what if humans had the same strength-to-weight ratio as ants? A 70-kilogram person would actually be able to lift 3,500 kilograms. That's like roughly the weight of a fully loaded truck or even an adult elephant. Every step would shake the earth like a mythological titan. Unfortunately, physics doesn't work that way. If we grew bigger while keeping ant-like strength ratios, our bones would snap, our lungs wouldn't get enough oxygen, and our hearts couldn't pump enough blood. The cost of ant-level strength is being ant-sized. In the end, ants teach us a profound truth. Real strength doesn't come from size, it comes from how we use what we have. They're not large, but through optimized design, efficient muscle use, clever engineering, and unmatched teamwork, they've become some of the strongest creatures on Earth, pound for pound. So the next time you feel small or powerless, think of the humble ant. It's proof that great power often comes in the tiniest of packages. If you found this story fascinating, share it with others. And if you're curious to learn more secrets of the natural world, stick around for the next episode.